Um, 8.1, check on learning. So here we are on our first problem. Most of these problems are just kind of going through the characteristics of exponential and exponential growth and decay functions. So here we go. It says consider the function 4x. I'm just going to kind of write it on the screen just in case we need it. 4 to the power of x and 1 over 4 to the power of x. Let's get rid of those. And so let's see here. How are the functions similar? So the functions have the same range, yes. Domain, yes, and x-intercepts. Yes. Because if you remember, I think they're both at like 1. So the growth comes up like this. And in green, the decay just goes the other way. Let's see here. The functions have the same range, domain, and y-intercept. That's actually what I meant. I didn't mean x-intercept. That was my mistake. Functions have the same domain and y-intercept. That's true, but they also have the same range, so. And the functions have the same domain and x-intercept, so that's false, because they don't actually intercept the x at all. Asymptote! So let's see, how are the functions differently? F of x, which is the first one in red, increases without bound as x increases without bound, while g of x decreases without bound, meaning forever. So there you go. So then let's see, this says, how does the horizontal asymptote of g of x compare to the horizontal asymptote of f of x? Select the words. So let's see here, g of x is a negative k, f of x is a positive k. So remember, our y equals k is our y asymptote. So, remember, y equals k makes a horizontal line at k. So then if k is negative, so the horizontal asymptote of g of x is the same distance below the x-axis. So if k is negative, then you're just going to have an asymptote at y equals negative k. Easy enough. These do get a little tougher, I promise. Graph of the parent function is here. Which of the following is the correct graph of the transformed function? So there's my parent function. So looking at this guy right here, the first thing that I notice is the asymptote is down at -4. And if you look at, they make this too easy sometimes. If you look at these pictures down here, the only one that has an asymptote at -4 is that one right there. That's all I needed to know to figure that out, which I think is whatever. They could do better. Boop. Okay, so this problem is a doozy. And part of it is that the textbook doesn't do a very good job of explaining how to do this. So I'm going to try it. So what it's asking us to do is find an equation for the graphed exponential growth function shown. And notice we have 2 reference points and an asymptote. So just like we did a couple chapters back, we're going to have to use those formulas, those generic formulas, or the variable formulas, to figure out, like what a, b, h, and k are, and then we can build our function out from that. So remember, for exponential functions, we've got a times b to the power of x minus h plus k. So let's start off easy. This k is easy to find. That's just our asymptote. I didn't even mean to match colors there. So the asymptote is y equals 1, so our k is going to be equal to 1. That's not too bad, right? So now we've got our 2 reference points that we can use to then figure out the rest of these. So the book gives us these formulas. So this one is totally fine. This one is not. So the issue with this one, I don't think it's wrong, but if our first reference point is 0, 1, their second reference point here is negative 1. So x is negative 1. So it's going 1 to the left. So that is different than what we have. So if we go back to our problem, we have our first reference point, and then we have 1 to the right. So that second formula is not actually going to help us. I did find the other one that we need to use, but we'll get to that in a second. So let's just start with our first formula. So here's our chart. This guy right here, I'm going to write that down. So first reference point is h a plus k. So our reference point is 2, 4. So that means that our h is equal to 2, and then our a and k. So remember, we've got k equals 1. So a plus 1 equals 4. A equals 3. Cool. So now the second reference point. So this chart, our second reference point is 1 to the left. So that's not going to help us. So after digging a little bit, I found this chart, which you will notice. So we've got our first reference point, same thing. But then we have our second reference point. Oops. Our second reference point is 1 to the right. So, or if we're talking about generic, it is 1 and then h to the right. So this is going to actually help us get to the right answer. So notice how the other chart had a over b plus k, whereas this one has a times b plus k. So this is what we're going to use. So our second reference point is 1 plus h. Oops. And ab plus k. All right, so let's go back to our problem. So 1 plus h, so we have h is 2, so that one should be 3, okay? That's our second reference point, so we're good to go. So now we can do this with this 10 right here, we can say, we know A, 3 times B plus 1 equals 10. So then 3B equals 9, then 9 divided by 3. So we can say our B equals 3. So once we have these, then we can make our formula. So it's going to be g of x can be equal to a, which is 3, times b, which is 3 to the power of x minus h. We'll go ahead and put this guy in parentheses, just for fun, for funsies. And then plus k, which is 1. So this is our final answer. So trust me, I tried it every single way with that other chart, and I couldn't figure it out. But once I found that different chart using those different reference points, all of a sudden it was, too easy, right? So let's type this in. To the power of x minus 2 plus 1. I forgot, this is not going to tell me if it's right or not. So let's check over here. There we are. Yeah, so here's our answer. Oh, I forgot to write it over here. H, there you go, 2. So it didn't seem like much, but I had to do some digging to find that right chart, so it is what it is. Alright, last but not least. So Jack purchases a new computer for $2,500. The value of the computer depreciates by 24% each year. When will the value of the computer be less than 160? Round your answer to the nearest whole number. So remember, the textbook gave us the rate of depreciation. I could come close to it, but I don't think I can remember off the top of my head. So it's a computer, it starts at one price going down, so you know that it's decaying. So our formula is going to be A1 minus R is the rate, times T. So now let's go back to our question. A is our initial value, so we've got 2,500. 1 minus our rate, which is 0.24. So I took that percent, turned it into a point. And I need to know, oh, wait. T. So let's see, it depreciates each year. And when will the value of the computer be less than? So I need to know when it's going to hit that 160 mark. So we are going to, we can simplify this a little bit. What is that going to be? 0.76 T is 160. So we're going to go check out our calculator. And you could minus this 160 over so that you're looking for zeros again. But it doesn't really matter. So we're going to plug this into our calculator, 2,500 I'm going to use parentheses because parentheses are my friend. To the power of x. So we're going to graph that. Now remember, my graph was like super crazy the last time I did this, so we're going to zoom in just a little bit. Okay, so now we're going to use our trace function, and our y here is the cost of the computer, our x is number of years. So I'm just going to keep going over until my y is roughly about 160. So at 9.6 or 10, somewhere in between there, I can also look at my table. That was around 10, right? Man, now I even forgot. So we're going to use trace again. Between 9 and 10. Okay. So our table, so our 9 is 211, our 10 is right at 160. That's what I kind of thought. So we can say at t equals 10 is when the computer is going to equal $160. Anything past that, it's just going to go down after that. So after about 10 years, and just to double check, after about 10 years. So there you go. Those are all 5 problems on Check Your Learning. I will see you in class, and good night.